easily as basically each service can be scaled independently of the others. Docker and Kubernetes further enhance scalability by providing containerization and organization capabilities. They provide resilience. So basically, microservices enable applications to be more resilient by allowing teams to isolate and fix issues within a single service without affecting the entire organization. Application. Docker and Kubernetes also provide fault tolerance and self-healing capabilities. Also, microservices enable teams to release new features and functionality quickly without having to redeploy the entire application. Docker and Kubernetes further enhance the agility by providing a flexible and scalable deployment model. And also they provide efficiency. So Docker and Kubernetes streamlines the development and deployment process by automating many of the manual tasks associated with traditional development and deployment. So let's start with an overview of monolithic architecture and its limitations. Basically, monolithic architecture is a traditional way of building software where all the code is written in a single code base and all the components are tightly coupled, basically. This architecture has a lot of limitations. Some of them are difficulty to scale. Basically, in monolithic architecture, scaling the application is challenging as the entire application needs to be replaced. Complex as the code base grows, it becomes harder to maintain and deploy the application. The whole code base is very fragile. A single bug can bring down the entire application. And and those are the main ones that are biggest limitations of the monolithic architecture. Now let's move to the microservice architecture. Microservice architecture is an alternative to monolithic architecture. In this approach, the application is broken down into small independent services, each with a specific responsibility. These services can communicate with each other via APIs. Basically, what are some of the biggest advantages of microservices over monolithic architecture? So for starters, scalability. Microservice architecture makes it easy to scale the application. You can scale individual services that are experiencing high traffic instead of scaling the entire application. It increases your flexibility. So basically each service can be written in a different programming language and the database can be specific to each service. This makes it easier to upgrade or replace individual services without affecting the entire application. Regarding the resilience, as each service is basically independent, a bug or failure in one service won't affect the entire application. Additionally, microservice architecture has built-in redundancy and backup mechanism that ensures that application is always available. Other benefits are faster time to market. Because of the smaller code base, it is easier to develop and deploy new features. And basically, in conclusion, microservice architecture is a modern approach to building applications that offer many advantages over monolithic architecture. It makes it easier to scale, more flexible, more resilient, and faster to market. Okay, let's start with how Docker works. So what is Docker? Docker is a containerization technology that allows you to create, deploy, and run applications in its containers. Containers are lightweight standalone and executable packages of software that includes everything needed to run an application, including code, libraries, and system tools. Basically, an example that is, you can imagine that you're building a web application that requires a specific version of Python and a specific set of Python libraries. With Docker, you can create a container that includes the correct version of Python and the required libraries. This container can then be deployed to any system that supports Docker, and the application will basically run the same regardless of the underlying system. What are some of the advantages of using Docker in DevOps? Basically, it provides you with a consistency because the Docker containers include everything needed to run an application. They are consistent across development, testing, and production environments. This basically makes it a lot easier to identify and fix any issues that you might occur during the development process. Basically, Docker containers can be run on any system that supports Docker, regardless of the underlying hardware of operating system. This makes it easier to deploy applications to different environments and reduce the risk of compatibility issues. Also, Docker makes it easier to scale applications horizontally by creating multiple containers of the same application. This will allow you to handle more traffic without putting strain on a single container. And lastly, Docker's resource efficiency, basically. Docker containers are lightweight and don't require a full virtual machine to run. This means you can run more containers on a single machine, reducing the need for additional hardware. So basically, Docker is a containerization technology that makes it easy to create, deploy, and run applications in containers. It offers many advantages in DevOps, including consistency, portability, scalability, and most importantly, resource efficiency. Okay, let's move on. So basically, Docker architecture consists of three main components: Docker daemon, Docker API, and Docker client. Docker daemons run on the host machine and manage Docker objects like images and containers and the networks. Docker API allows communication between the Docker client and Docker daemon. Docker client is the command line tool that is used to interact with the Docker daemon. What are some of the key components of the Docker? Is basically Docker image. Docker image basically is a lightweight standalone and executable package that includes everything needed to run an application, including code, libraries, and system tools. Docker images are built different from a Docker file, which is a script that defines the step needed to create an image. Next one is Docker container. That is also a lightweight standalone and executable package that runs on the top of the Docker image. Containers can be created, started, stopped, moved, and deleted. Containers are basically isolated from each other and from the host system, which makes them a secure way to run an application. And a Docker registry. Docker registry is a repository for storing Docker images. The Docker Hub is a public registry that hosts thousands of Docker images, but you can also create your own private registries. And what are some of the Docker engine components? Those would be Docker CLI, Docker API, and Docker engine. Docker CLI basically is a command line tool that is used to interact with Docker engine. Docker API is used to communicate with the Docker engine. And the Docker engine is the underlying technology that allows containers to be created, managed, and run. So basically, Docker architecture consists of three main components: Docker daemon, Docker API, and Docker client. Docker images are lightweight, standalone, and executable packages that include everything needed to run an application. Docker containers are packages that run on the top of Docker images, and Docker registry is a repository for storing Docker images. All right, we can move on. Docker images are a critical component of the Docker ecosystem, and they allow you to package and distribute your application in a self-contained portable manner. To build a Docker image, you will need to create a Docker file. A Docker file is a script that contains instructions on how to build your Docker image. It specifies the base image, the environment, the dependencies needed, and the commands to run your application. Next is to build your Docker image. Once you have created your Docker file, you can build your Docker image using the Docker build command. This command will read the instructions from your Docker file and create a Docker image from them. And lastly, pushing Docker images to your Docker hub. After you have built your Docker image, you can push it to the Docker hub or any other container registry. This will allow you to share your Docker images with others, making it easier to distribute and deploy your applications. Basically, building Docker images may seem daunting at first, but it's relatively straightforward once you get the hang of it. And with this, we have finished with the Docker. Now we will move to the Kubernetes. So basically, what is Kubernetes? Kubernetes is an open source container orchestration platform that automates the deployment, scaling, and management of containerized application. Kubernetes was originally developed by Google and is now maintained by the Cloud Native Computing Foundation, in short CNCF. Basically, let's take a look at how basically the Kubernetes works exactly. Basically, Kubernetes works by managing a cluster of nodes, where each node runs a containerized application. A node is a working machine that runs on one or more containers. Kubernetes uses a master node to manage the cluster and a set of worker nodes to run the application. Basically, Kubernetes allows you to define the desired state of your application using a declarative approach. You can basically define how many replicas of each container you want to run, how much CPU and memory resources each container requires, and basically how to deploy updates to your application without any downtime. Now, what are some of the advantages of using Kubernetes in DevOps? Basically, Kubernetes allows you to scale your application up or down based on the traffic demands. Kubernetes ensures that your application is always available by automatically rescheduling failed containers and replacing them with new ones. Kubernetes has a lot of fault tolerance. It will ensure that your application can tolerate failures by automatically restarting failed containers. Kubernetes also allows you to deploy your applications to any cloud provider or on-premise data center. And lastly, security. Basically, Kubernetes provides several security features such as network isolation, encryption, and role-based access control. So basically, in conclusion, Kubernetes is a powerful tool for managing containerized applications in DevOps. It provides a lot of benefits for DevOps teams, such as scalability, high availability, fault tolerance, portability, and security. The architecture of Kubernetes is basically designed to be scalable, fault tolerant, and extensible. It consists of the master branch, master node, and the worker nodes that are responsible for managing and executing containerized application. Kubernetes cluster is a set of nodes that work together to run a containerized application. The cluster consists of a master node and worker nodes. Nodes are individual machines that make up the Kubernetes cluster. They can be physical or virtual machines, and they run the applications in their containers. Pods are the smallest deployable units in Kubernetes. A pod consists of one or more containers and shared storage and network resources. They are the basic building blocks of the application and are created and managed by the Kubernetes system. Services, basically services provide a stable IP addresses and DNS names for a set of pods. They allow multiple pods to be addressed by a single IP address, which simplifies communication between the pods. And lastly, deployments. They provide a way to manage the life cycle of pods. They define the desired state of the application, including the number of replicas, and automatically update the pods to match the desired state. So basically, Kubernetes master and worker nodes. The master node is responsible for managing the Kubernetes cluster. It runs the Kubernetes API server, controller manager. The API server is primary interface for interacting with the Kubernetes system, and the controller manager ensures that the desired state of the cluster is maintained. etcd is a distributed key value store that stores the configuration data for the cluster. Now, Kubernetes worker nodes are responsible for running the containers that make up the application. They run the Kubernetes agent, which communicates with the master node to receive instructions on which containers to run and how to run on them. So, in conclusion, Kubernetes architecture is designed to be scalable, fault-tolerant, and extensible. It basically consists of master node and working nodes that work together to manage and execute containerized application. Okay. A Kubernetes deployment is a resource object that manages a set of replicated pods. It defines the desired state of the application, including the number of replicas, and automatically creates or deletes pods to match the desired state. So how can you create a Kubernetes deployment? You can write a YAML file that defines the deployment object, including the container image, number of replicas, and other configuration settings. You will then use the kubectl command line tool to create the deployment object from the YAML file. And lastly, we will verify that the deployment is running correctly by checking the status of the deployment and its associated pods. Kubernetes deployments makes it easy to scale the number of replicas up or down to meet the needs of the application. If you want to scale a deployment, you can use the kubectl command line tool to update the deployment object, specifying the new number of replicas. Then Kubernetes will automatically create or delete pods to match the desired state of the deployment. And then you can verify that the deployment is running correctly by checking the status of the deployment and its associated pods. Kubernetes deployments support rolling updates, which allow you to update the application without any downtime. You can create a new version of the container image and push it to the container registry. Update the deployment object with the new container image version. Kubernetes will then automatically create new pods with updated container image and gradually terminate the old ones. And lastly, you can just verify that the new version of the application is running correctly by checking the status of the deployment and its associated pods. So basically, Kubernetes deployment is a powerful tool that simplifies the process of managing and scaling containerized application. With Kubernetes deployments, you can basically and easily create, scale, and update your applications without any downtime. As we said before, Kubernetes services is a way to abstract away the details of individual pods in a deployment and provide a stable IP address and DNS names for clients to connect to. Services act as a load balancer, distributing incoming traffic across a set of pods that provide the same functionality. To define a Kubernetes service, you need to create a YAML file that will define the service object, including the name, selector, and port configuration. Use the kubectl command line tool to create the service object from the YAML file, and verify that the service is running correctly by checking its status and endpoint information. Kubernetes services come in 3 different types, each with a different behavior and use case. First one is cluster IP, the default type of service that provides a stable IP address and DNS name for pods within the cluster to connect to. Second one is node port, a service that exposes the pods to the outside world by mapping a port on each node to be a port on the service. And third is a load balancer, a service that provisions a load balancer in a cloud provider to distribute traffic to the pods. Service discovery is the process of locating a service and its associated endpoints in the Kubernetes cluster. Kubernetes provides 2 ways to perform service discovery. First one is through the DNS. Kubernetes runs a DNS server that maps service names to their corresponding IP addresses. Clients can use this DNS server to resolve service names to their IP address. And second one is environmental variables. Kubernetes also sets environment variables for each service that include the service name and IP address. Clients can use these environment variables to connect to the service. So basically, Kubernetes service provides a stable IP address and DNS names for clients to connect to, abstracting away the details of individual pods. In a microservice-based application, configuration data can quickly become complex and difficult to manage. Kubernetes provides 2 objects that can help us manage configuration data. First one is config maps. Config maps are used to store configuration data as key value pairs. These can include environmental variables, command line arguments, or any other configuration data that the application needs to function correctly. And the second one is secrets. Secrets are used to store sensitive configuration data such as passwords, API keys, or TLS certificates. Secrets are stored in an encrypted format and can only be accessed by authorized users. To create a config map in Kubernetes, you need to create a YAML file that defines the config map object, including the name, data, and any other configuration options. You will then use the kubectl command line tool to create the config map object from the YAML file. And lastly, as always, you verify that the config map is running correctly by checking the status and the data information. To create a secret in Kubernetes, you also need to create a YAML file that defines the secret object, including the name, data, and any other configuration option. Use the kubectl command line tool to create the secret object from the YAML file, and then As always, verify that the secret is running correctly by checking its status and data information. So basically, Kubernetes and config maps are Kubernetes config maps and secrets are critical components that allow us to manage configuration data in our Kubernetes cluster. Config maps are used to store configuration data such as key value pairs, while secrets are used to store more sensitive configuration data. Kubernetes volumes are a way to store and manage data in your application. They are a special type of directory that can be mounted into a container and can be used to store data that needs to persist beyond the lifetime of that container. When a container is terminated, any data stored in a volume will still be available to other containers that use the same volume. There are several types of volumes in Kubernetes. There is empty dir, basically empty directory. This type of volume is created when a pod is created and it's deleted when the pod is terminated. It can be used to store temporary data that needs to be shared between containers in a pod. Other types of volumes are host path. This type of volume moves a file or directory from the host node's file system into your pod. This can be useful for accessing configuration files or other data that is stored on the host node. We also have config map, we covered them, and secret. And finally, we have a persistent volume. PV is a storage resource in a cluster that can be used by multiple pods. Persistent volumes are created by administrators and can be dynamically provisioned by storage classes. Pods can consume these volumes through persistent volume claims, PVCs, which act as a request for a specific size and access mode. PVCs can be created by developers and are used to abstract the underlying storage details from the application itself. In Kubernetes, networking allows different parts of the cluster to communicate with each other, including communication between nodes, containers, and services. Kubernetes networking is based on the concept of a network plugin, which is responsible for managing the networking rules and policies for your cluster. Kubernetes DNS is an important aspect of Kubernetes networking, which provide a way to resolve a domain names of services within the cluster. When you create a service in Kubernetes, it gets assigned a DNS name that other pods in the cluster can use to communicate with it. And network policies provide basically network policies provide a way to control the traffic that flows between different parts of the cluster. Basically, you can use network policies to specify which pods can communicate with each other and which ports they can use. This will help you to increase security and prevent unauthorized access to your own cluster. Basically, monitoring your Kubernetes cluster is crucial for understanding its health and performance. Kubernetes provides various tools for monitoring and debugging of your cluster. Some of the popular tools are Prometheus, Grafana, and Kubernetes Dashboard. Kubernetes provides various metrics that can be used to monitor the health of your cluster. These metrics include information about the state of the nodes, pods, and containers. Prometheus is one of the most popular tools for collecting and querying Kubernetes metrics. Logging is an essential part of monitoring your Kubernetes cluster. Kubernetes provides different logging options, such as writing logs to a file, sending them to a centralized logging system, or exporting them to a logging service. Some of the popular logging solutions for Kubernetes are Elasticsearch, FluentD, and Kibana. So let's move on to continuous integration and continuous deployment with Kubernetes. CI/CD is a software development practice that automates the entire software delivery process. CI/CD aims to reduce the time and effort required to deploy code changes into production by automating the build, test, and deployment stages of the software development process. Continuous integration with Kubernetes involves automating the build and the test stages of the software development process. The main goal of CI with Kubernetes is to ensure that the code changes made by developers are integrated into the main code base and tested automatically before being deployed into production. Kubernetes provides a flexible and scalable environment for building and testing applications, and it supports a wide range of tools and technologies that can be used for CI/CD, including Jenkins, GitLab, and Circle CI. And finally, continuous deployment with Kubernetes involves automating the deployment stages of the software development process. The main goal of CD with Kubernetes is to ensure that the code changes made by developers are automatically deployed into production without any manual intervention. Kubernetes provides a powerful platform for automating the deployment process, and it supports a range of deployment strategies, including rolling updates, blue-green deployments, and canary releases. So in summary, CI/CD is a powerful practice that can help you streamline your software development process and reduce the time and effort required to deploy code changes into production. With Kubernetes, you can easily implement CI/CD workflows that automate the entire software delivery process from building and testing to deployment and monitoring. So basically, in this workshop, we have covered several key topics related to microservices, Docker, and Kubernetes in DevOps. We have discussed the benefits of using microservice architecture, the basics of Docker containers, and the advantages of using Kubernetes for container orchestration. We have also looked at how Kubernetes can be used to manage configuration data, volumes, networking, monitoring, and logging, as well as how it can be integrated into a continuous integration and deployment CI/CD pipelines. Here are some of the key takeaways from this workshop. Number one, microservice architecture provides Microservice architecture provides you with several benefits over monolithic architectures, including scalability, modularity, and fault tolerance. Docker containers provide a lightweight and portable way to package and run applications. Number three, Kubernetes provides a powerful platform for managing containers at scale, including features such as auto-scaling, load balancing, and rolling updates. Kubernetes config maps and secrets can be used to manage configuration data and sensitive information such as passwords and API keys. Number five, Kubernetes volumes provide a way to store data outside of containers and to share data between containers. 6 is Kubernetes networking allows for a secure communication between containers, and Kubernetes DNS enables service discovery within the cluster. Next, we have Kubernetes metrics and logging. It will provide you insights into the health and performance of the cluster and applications running on it. And lastly, we have a key takeaway about how Kubernetes can be integrated into a CI/CD pipeline to automate the building, testing, and deployment of an application. Here you will have some resources for further learning if you're interested in this. And I think this would be all. Now, does anyone have any questions before we end this session? Suppose that no one has any questions. So we can end this workshop now. Thank you all for joining me in this workshop on microservices, Docker, and Kubernetes in DevOps. I do hope that this presentation has provided you with a good understanding of the fundamentals of these technologies and how they can be used to improve your development and deployment processes. Of course, if you have any further questions or would like to learn more, feel free to reach out to me or to check out the resources I have provided. Good luck, everyone, and thank you for your attention.